Testing, 1, 2, 3, testing. In chapter 6, we discuss the cosmic distance ladder, which is a series of techniques, I guess you can say, for determining the distance of a celestial object. The first rung on the ladder is parallax, and I gave the example in the book where if you hold your finger up and try to look at something behind your finger, and you can move either your finger or your head, and you notice that if you close one eye or as you move, or it's different than if you close the other eye. Like you can tell that there's a difference. Well, the angle of deflection can be used to determine the distance of whatever object you're looking at that's behind your finger. And the same thing can be done with two stars. So we know how far Andromeda is, and so you could use parallax for that. I mean, that's not really, I don't think you might be able to use Andromeda for the local neighborhood. That would be interesting to look. I don't do any astronomy, so anyways, but I think it's more of like stars, like you can use Sirius or other stars in our galaxy to find the distance to another star. But you might be able to do galaxies. It seems like you might be able to do that. Just for short distances though. But I'm sure you could use radio astronomy or something like that to determine distances between, nearby galaxies with Andromeda. That's probably difficult though, I would guess. Anyways, let's get on to Cepheids and supernova. So, Cepheid or Cepheids, I don't know how you say it. These are the second rung of the ladder. And so they have there's a time element with both Cepheids and supernova. Cepheids have they blink, I guess, as they pulsate. And so you can determine the distance using that, the difference between the apparent magnitude and the absolute magnitude. There's an equation. I think I've got the equation below. I'm actually going to be, you're watching the, me develop the thing. So you'll just have to, pause and look at it. There's a link in the description though, if you want to just open it up. I'm on a laptop, and that's basically the only time I ever experienced the internet is through a laptop. So you people on your phone, I don't know how y'all do this. Just buy a laptop. Anyways, so Cepheid variables pulsate, and because they pulsate, then you can measure the distance between each pulses and calculate it. And with supernova, you have a light curve, basically. You can see the peak luminosity, and they know that, and then as time passes and it declines, then that gives them more data, and they can line it up and figure out how far it is using that. And so the next rung on the ladder is the Tully-Fisher relation, and so that's basically when you have like enormous galaxies, like a spiral galaxy, and these are brighter because there's more stars, so there's more light bulbs, and so they're spinning faster too, and so they can determine the apparent magnitude and the absolute luminosity and all of that. And they can use that to determine the distance with the Tully-Fisher relation. So there's a pretty simple equation for that. I mean, none of these are simple equations really, but for one, you gotta determine the mass and things like that. So it's difficult to be 100% certain at this distance. This is where it starts getting a little fuzzy. There's a little bit of assumptions you gotta make, and got to make sure that you're dotting your I's and crossing your T's. But then the next rung on the ladder is the one I want to focus on for a moment. That's like I dwelled on it just for a little bit in chapter 6. It's the angular diameter distance. And so there is this odd thing that happens with high redshift objects. Usually the larger an object is, the closer it is to you. But in cosmology, there's this weird thing where it changes, it switches at some point where the larger an object is, because there's the geometry of space-time is such that it causes the objects to appear larger. I think this happens around z equals 1.5 or something like that. Z equals 1.6. And the interesting thing, now this is basically overlooked in cosmology, but both Wald and Binney, and I forget the other two authors, but both of those co-authored papers, that describe this angular diameter distance from gravitational lensing. And so you don't need expansion for this to happen. This is amazing for me. And this was an amazing find for me. I've got the two sources and there's others. There's actually other published papers talking about this. It's what made it a little confusing for me was that there's, in their papers, they talk about an inhomogeneous cosmology or inhomogeneous metric. And every time you look at a star, it's inhomogeneous. And so that's the thing, is that there's already been inhomogeneous cosmologies. Like, people have developed this. There's the Tolman-Bondi metric. There's several other, inhomogeneous distributions. And so the idea is basically, what if the Earth was in the center of a ring or something like that? And when you're looking, but see, that's this is why it's kind of silly to model the universe. You're modeling the geometry between a star and the telescope, or your eyeballs. That's what you're modeling. You're modeling the null geodesic. If you try to model the entire universe, it's, like, you can do that, but it's better to use data and then do it. That would be ideal. You definitely don't use a homogeneous mass distribution, because that's not accurate. It's not accurate. I mean, especially you're not going to use a homogeneous mass distribution when you're looking at a star or a galaxy, because that's not that's not the situation you're doing. So you don't use a cosmological model for that. Anyways, so the fact that I can recover the angular diameter distance relationship using my distribution, this 2K, and they align, that to me is amazing. Like, that was a wonderful discovery for me, because I was nervous when I first started investigating ADD years ago, because I was thinking that, I was like, man, this is kind of hard to figure out. Like, why would it be like this? And I thought that the geometry would be the same with gravity, that gravity couldn't do the same, but like, I couldn't find how to do this, and I didn't know how to do it. But luckily, Wald and Binney both published two different papers. Or not, I don't think Binney published his paper, but I'm sure Wald did. And there's others that I found. But anyways, so let's do a review. The way I approach this is that there are two assumptions in lambda cosmology that I disagree with. One, the universe is expanding, and two, the universe is homogeneous. If you just fix both of those in one swoop by assuming that the cosmological redshift is caused by gravitational redshift, and then develop your distribution from that, it perfectly aligns with observations. So the mass of R, or the mass at R, or the mass at the distance R, equals 2 pi kr squared, where k is this coupling constant, and it's 0.833 kilograms per meter squared. So that gives us the distribution for our universe. It's isotropic. It's not homogeneous. That's the wrong way to think about it. Mass density is scale dependent in this universe. This metric is observer dependent, and we have an observer dependent horizon. Observer dependent means the observer is centered in our metric. This, there's the Copernican principle, and it's also part of the cosmological principle, there's this idea that we shouldn't be in a special place. You can't just say that some place of the universe is different than the other. But this is observer dependent. So the specific geometry of the observation depends on your relationship to the star. So the amount of gravitational redshift depends on your distance to the star, your distance from that star. And that's this R that I keep saying. And so the total mass for a star that you're looking at is 2 pi k R squared. Automatically built into that is an observable limit. And this observable limit is pretty much the same as the Hubble limit in lambda cosmology, around 13.7 billion light years or something like that. It's 1.289 times 10 to the positive 26 meters. At that distance, the amount of mass, which is like 8.5, I think it's 8.6 times 10 to the 52 kilograms, that much mass means that it's a Schwarzschild metric. It means it's a Schwarzschild horizon. It's equivalent to the Schwarzschild horizon. It means that there's so much gravitational redshift you can't see that star beyond that, because there's too much mass between you and that star, and the geometry shifts that null geodesic between that star and you towards the star, I guess is one way of thinking about it. But we have this horizon. And so at this horizon, it's basically, you're looking at a star that is 13 billion light years away from you, and it's right there close to the horizon. And then there's a star directly behind it that's beyond the horizon, okay? When I say star, I'm talking about galaxies. That's fine. Galaxies, same thing, but the star is what's producing the light. But you're looking at a galaxy. Right there at the horizon, there's 2 galaxies, one beyond the horizon, one close to you. At the horizon, there's Hawking radiation emitted. You can calculate this. It's a very simple calculation. I mean, it's not too simple, but it's the temperature at the horizon is h bar. For my calculation, like, this is different than the Hawking radiation calculation, but it's the same thing. I'm just implementing my coupling constant, but it's h bar g k divided by c times the Boltzmann constant, and that'll give you temperature at the horizon. But then you got to do the blue shift, and so at the horizon, it's emitted at something like 1.4 times 10 to the negative 30 Kelvin. It's very, very cold at the horizon. But because we're not talking about a star, we're talking about just the horizon. So just to where this K, this coupling constant, the further out you go, it builds mass. And so if you're talking about a star, it's gravitational redshifted. But if you're just talking about empty or space or some dust or something like that, then you are more massive. You are the center of mass now. The observer is the center of mass. And so this is blue shifted. And it's amazing because in order to get the 2.725 Kelvin, it's at 2 Planck lengths, 2.15 Planck lengths, but that's adjustable by the Hubble radius. And so the coupling constant, the Hubble radius, all of this can be fine-tuned, but it's an observed thing. Like, it depends on the Hubble constant. You measure the Hubble constant, and it'll change the coupling constant a little bit if you change the Hubble measurement. If they come out tomorrow and say it's 75, then it would change the coupling constant a little bit, and it would actually change the distance from the horizon. And right now, it's at 2.15 for 72 kilometers per second per megaparsec. That's for that Hubble constant. And so at that distance from the horizon, that's how you get the observed temperature in the cosmic microwave background, that 2.725. Whoa. That was a mouthful. I get excited about that one because that, to me, like, it's so amazing. It's such a perfect fit. It's better. It's better than lambda cosmology's explanation. And I can explain the anomalies. Well, I can, I have a hard time explaining anything. But I'm pretty sure that it changes everything about the anomalies, because one of the things about the anomalies is that it seems that the structure is what's causing the anomalies. And so the structure of the universe is, if the geometry of the universe is actually what creates the horizon, then the structure of the universe is very relevant. It's not just the past that's relevant. And then the other piece of evidence is this angular diameter distance relationship. I mean, this just perfectly aligns. You use this coupling constant K, you plug it in and use the gravitational lensing, find the angle of deflection. Boom, it just perfectly lines up with the ADD. Like, so the ADD redshift relation, it just works out exactly the same as with lambda cosmology. It's amazing. There's a little bit of a difference in the high redshift Z's, but I think the ADD starts becoming irrelevant the closer to the horizon you get. So that's the evidence so far. In the next chapter, I discuss dark matter and dark energy.